Great. Hello, everybody. So welcome to the seminar between Cardiff University and University of Wyoming. So I think people are slowly coming in. We have just a couple of matters of housekeeping. We have a question and answer box right at the end. So if you have questions, please post them there. So my name is Omar Rana. I'm the Dean of International for Physical Sciences and Engineering at Cardiff University. And interestingly, we've just signed a partnership with the University of Wyoming about 2 days ago. We have now a strategic partnership and a special fund, strategic partnership fund. And I'll start by a quick 1 minute, 36 seconds exactly video just to highlight the partnership itself. So I'll just play this.
Well, the partnership with the University of Wyoming is really important to us. The reason that we went down this particular route is because there are pre-existing academic collaborations, and what we're doing really is building on that really strong foundation and bringing those collaborations together into an institutional strategic partnership, which I think will be of enormous benefit to both sides. Well, we've looked forward to this for a long time. We've been building the relationship for the last 2.5 years, and today's signing just means that we're ready to roll, and we have a lot to do, both from our faculty and for our students and for our staff. And it's a big partnership that's very important for us and for the state of Wyoming.
Great. So I just wanted to give you this context. So it's a pleasure to introduce the two speakers from today. So we have Professor Eugene Holubnyak from the Energy Resource Center, and my colleague from Cardiff, Dr. Meysam Qadrdan. So hydrogen is a very interesting new area for energy for virtually everybody in the world today. So both hydrogen generation, hydrogen transport, and hydrogen storage is playing a major part, not just here in South Wales, but I know it's a very important part for the US, especially the hydrogen hubs that the NSF and other institutions are planning to launch. So we have collaborative projects between Cardiff and a variety of other partners. So we'd really like to highlight this today. And most importantly, we are looking for collaborative work between the people who are joining this call and how we could work together. So I'll pass over to my colleague, Eugene, for starting the presentation. Eugene, over to you.
Thank you, Omar. I'm excited about this collaboration. And we, just like Omar was saying, is that we are started this seminar series just to kind of find the common ground and find the better place where both entities could collaborate. And I'll have just a brief overview of what University of Wyoming and Hydrogen Energy Research Center at the School of Energy Resources has been doing in this area. It's going to be just kind of very, very high level overview of different activities and different areas that are of interest to us, and where we are thinking about is expanding research and doing more. And so hopefully, after we also hear from my colleague Meysam, we'll see more sort of commonalities and more areas on which we can collaborate. And then we will have actually more people from our universities present their research, and hopefully in this process we'll find even more common ground. So let me share my slides. Can you see my slides? Is everything working fine?
Yes,
all right.
That's
great. Well, so today I will be talking about hydrogen hubs and energy infrastructure as it relates to Wyoming, and as we as an entity see it as a hydrogen energy research center, and as a School of Energy Resources, we are kind of unique place on campus, School of Energy Resources. We are part of campus, but then at the same time, we have a very specific mission. And this mission is energy-driven economic development for Wyoming, and this is what we are focusing. It doesn't mean that we cannot go beyond Wyoming. It means that we need to bring research that is and development of different projects that is very relevant for our energy-driven mission here in the state. So this is a brief outline. I'll briefly talk about what Hydrogen Energy Research Center is and a team, and then I will outline why it makes sense actually to have hydrogen infrastructure, hydrogen production, storage, and the distribution network, and also use in Wyoming. So Hydrogen Energy Research Center was stood up just recently. It's a little bit over a year that it exists, and I became a director just recently, basically March of last year. And what we think the center needs to study is that creating hydrogen from Wyoming natural resources, vast natural resources of Wyoming. We also need to understand how we move hydrogen about. Water is obviously a very sensitive issue for our state. We need to be very cognizant about that, and we'll strive to understand how to use it better, how to be better stewards of this resource. And then, of course, techno-economic analysis and market evaluation, and understanding why it actually makes sense to produce hydrogens in Wyoming is one of those key areas that where we are focusing our efforts. So we have several projects that are kind of constitute the center at the moment. This is the net zero hydrogen scenario for Wyoming, funded by Department of Energy. And here's a team. So I'm not doing it alone. And there's a number of things that I will be talking about that is coming exactly from this research and from this team. So we have people like Cudington, who's our policy specialist, and Kara Formstrom that has joined us recently will be added here as well. So we have resource specialists like Scott and Fred and Charles, and we have economists like Tim Considine, and we have life cycle analysis and modeling specialist as Haibajai and his postdoctoral student Manish. And also Casey is working with Tim Considine. Tiffany Bishop is helping to manage the project, and Holly Krutka is our executive director at the School of Energy Resources. Here's the excerpt from our team at our website. Our team will be growing. At the moment, we have a research scientist that just recently joined us, and she will be studying energy economics and water issues specifically. And we also have research affiliates from within the university, and some of them are specialists in things like geomechanics, and some of them are geochemistry specialists, economics, life cycle analysis, and so on and so forth. So it's this affiliate program is growing, and so more people will be joining in the following months. We also have appropriation from a special appropriation from the state with a total budget of about $650,000 to fund 7 projects. All those projects are currently ongoing. There was a call for proposals on how we use hydrogen. And here are the projects and their focus areas that are funded in the first round of funding. So you see the range of topics. It's there's geochemical reactivity, there's phase behavior, there's economic analysis, There's growing geomechanical lab at the university, making sure that we have that capability moving forward. There's also wind energy use and hydrogen and electrolysis analysis. And then we have technological learnings and resource estimation for the blue hydrogen specifically. And then we are also looking into storage options. And in this particular case, it's salt caverns or trona mining with the petroleum engineering department. So range of topics. We would fund more if we had more funding. There's more talent. There's more interest at the University of Wyoming, and so hopefully we'll have another round of funding, and we'll see if we can identify even more research areas that we can grow. Here are the beautiful people that constitute this program. So the ecosystem is growing, and we together are applying for various Department of Energy and NSF funding. We applied last year, and then we have plans to apply this year as well. So why it makes sense to study hydrogen and actually make hydrogen in Wyoming? Wyoming is an energy state. We are a net energy producer and very important energy producer in the United States. So we're #1 coal producer and very high up in crude oil and natural gas. And so we produce a lot of natural gas that we then feed to California, Nevada, Oregon, and Washington. These are kind of our primary recipients of our hydrogen. And of course, energy economics is our underlying part of the economy, and constitute a lot of resources and the revenues coming in the state because of that. And of course, royalties are very important for our sustainability. And with this changing landscape that is around us, we see that states like California, Nevada, Oregon, and Washington are striving for renewable portfolio standards and clean energy standards. They're establishing them by policy means, and so we will see a change in what constitutes the energy markets around us and in our main consumer states of the energy that is produced in Wyoming. There are other policy considerations for this. There are natural gas bans again in the states like Washington and California. Of course, there's also voluntary things that stimulate the hydrogen economy, things like carbon markets. And with that, I can actually talk about a little bit about the success story and how it relates to hydrogen. Is that natural gas production, if we in the future, if we instead of natural gas, we substitute at least part of our portfolio with hydrogen, that would be great. But also today we see that because of the changing markets, our behavior in Wyoming and sustainably sourced gas is one of those things that we're very proud in the state. And because of the research that was done at the School of Energy Resources and the University of Wyoming, and because of the market forces, and because producers within the state take it upon themselves to lower the emissions, today natural gas sourced in Wyoming is one of the most sustainably sourced sources of natural gas in the United States. And so we hope that this is a similar situation that is going to happen with hydrogen, and part of that energy portfolio becomes hydrogen production. Another reason to study hydrogen is that energy security, energy sustainability is very important for us and as our vision and moving forward. And so if we learn from lessons from other states, things like this bomb cyclone, or the weather event, where a lot of demand was placed on the grid to generate energy in eastern states. And during this event, we have learned that the backbone of energy generation is very important, but also if we do have storage capacities for the grid where we can tap into during those difficult stages of grid existence, then we do have better security and better sustainability for the energy production. And hydrogen is one of those energy carriers that is better than regular lithium-ion batteries and a lot of other energy carriers to store energy for a long time. This means not only days, but also months and months worth of electricity for consumers. And we can store them in geology, and we do understand geology. This is one of our very strong areas of expertise here. With the CCS and also oil and gas expertise that the University of Wyoming and School of Energy Resources has developed. So we understand where and how we can do this, and we can do it in domal salts, bedded salts, and hopefully maybe at some point in porous reservoirs, like abandoned oil and gas reservoirs, or reservoirs that were cited for the natural gas storage. At the moment, we don't know how to do this specific thing, but we do know bedded salts and things like trona mining is very similar to that. So we hope we can understand this resource better. We also are trying to understand what is the most sustainable, but also what is the cheapest and more reliable way to produce hydrogen. In this case, blue hydrogen and hydrogen produced from natural gas with CCUS is very attractive model for us. So we're looking into this model, and we are looking on how to improve it. What is more sustainable for our state. And we're not just theorizing; it's also in collaboration with multiple entities. We do have projects with Department of Energy and multiple other entities like national labs such as Idaho National Lab, NREL, and Los Alamos, and then Tallgrass and Schutz Williams and Jonas are the companies that we work with in terms of cooperative project development. And so we understand this firsthand on how those projects are put together. So we have sort of not just a theoretical background, but also hands-on experience. Another very important issue is water consumption for hydrogen. And although it is compared to other uses, hydrogen production is not a huge consumer of water. At the same time, because we do live in a state that has a very arid environment, and also because of other competitive uses such as in agriculture and industrial use and municipal use, it is a very sensitive topic. And so we want to make sure and emphasize that a lot of projects will actually repurpose the water uses that are already in place. So there's not going to be a lot of demand for new water, but also we are trying to find new sources that make sense for the state. We also understand that for things like electrolysis, water production, water is a critical element, and it could be challenging for some of the operators, some of the producers to actually use and utilize water in general. So because there is a cooling component for the electrolysis, and also because there is a cleaning component for the electrolysis process, that kind of gives provides some of the challenges on moving forward. Things like waste disposal could be tricky for some of those producers, but at the same time, if we have to treat this water for all of those uses such as electrolysis or gasification or natural gas based production, then there's a possibility to actually create new industry that actually treats water specifically for hydrogen. And we have seen those things in other places, like I'm providing the Permian Basin example, where you have $4 to $5 billion in annual revenues. Industry that sprung up in the Permian Basin that treats water, that provides it for fracking and oil and natural gas production. Also, we're looking at markets in general. What would it take to displace the transportation fuels in the state of Wyoming in case this moves forward? Maybe Wyoming is not the best state, but there's a lot of fuel to displace, because we do have a lot of transitional space, because we have both rail and interstate system that moves a lot of cargo through our state, and so that could make sense as well in terms of the transportation and providing the infrastructure, maybe with hydrogen as well. And then we also know that some of the coal generation capacity could be displaced in the near foreseeable future. And if it's going to be displaced, does it make sense to retrofit some of those facilities with hydrogen generation facilities? We also understand that investment in the space is tricky, and that because of the how expensive those projects are, then what kind of infrastructure they will require. There's some sort of investment hesitancy, and there are ways to solve this, but at least we now know, that this problem actually can exist, and why some of the projects might not move forward. Another important consideration is, of course, ability to move hydrogen. As I said, Wyoming is an energy exporter. We export a lot of energy, and so we need to have the pipeline network connection, but and other means of moving hydrogen around us. And so we do have that. We also have a pipeline corridor initiative that could help grow the infrastructure. But not only that, but also the CO2 is an important component. If we do produce hydrogen with the blue method, which I strive not to use the colors, but basically production with the fossil fuels will require CCUS component. And if it requires CCUS component, it's great to have CO2 available for you to move CO2 through the pipeline network in case you don't have sufficient geology in the place where you produce your blue hydrogen. But we also understand that maybe it's not going to happen immediately, the pipeline, meaning the pipeline network, not only for CO2, but also for hydrogen. And we foresee that a lot of this first mobilization is going to happen through rail. We see those examples elsewhere, places like Bakken, where it was estimated that a lot of this crude will be loaded through the pipeline network, but actually what happened is that railroads moved oil first and continue moving it to today as well. And Wyoming dominates rail, and so we believe that this component is very important too, and we will be able to ship our hydrogen to our consumers in other states through rail system as well. There's outreach is very important for us, and collaborations with Cardiff was one of those things that we strive to do. And here's a list of stakeholders we reached out to. Some of them we already are calling partners. Some of them will become partners in the near future, specifically on hydrogen. We collaborate with many of them on other aspects, but hopefully hydrogen will become one of those places to collaborate with all of those entities as well. And Christina, who's organizing this seminar, is doing a lot on the tribal outreach. Reaching out to those communities is very important to us, and so there's a number of activities that we conduct in this area, and growing this relationship is very important to us. And hopefully, we'll have some of the projects that also are on tribal lands, and hopefully we can support those projects moving forward. And so with that, I think I'll take questions later, and I'll give it the baton to Meysam.
Thank you, Eugene. Thanks, Meysam. Or to you.
Yeah, sure. Let me just. Can you see my slide okay?
Yep.
Excellent. Thank you very much. Hello, everyone. Good afternoon to those colleagues connected from UK. Good morning to our colleagues connected from North and South America. My name is Meysam Qadrdan from School of Engineering, Cardiff University, and I'm very happy to use this opportunity to talk to you about the research that we are doing on hydrogen. In particular, in this talk, I would like to focus on system integration of hydrogen. So before I actually start the presentation, I just thought it might be useful to say a few words about the background of this slide. So it is called Climate Stripe, and each stripe actually shows how temperature in 1 year can be compared with a long-term average temperature in England. And those colors, which are red and closer to red, means the temperature in that year was higher than the average long-term temperature, and those blue colors means years in which temperature was below average temperature. So from left to right, we are moving from 1,800, and here to the right we have 2015. And as we can clearly see, the temperature is rising, and the frequency of having above long-term average temperature is increasing. This is exactly why we are working on this topic of net zero and decarbonization of energy systems. So the outline of my presentation actually is shown here. I would like to start with a very brief introduction of myself and the research centers I'm part of. I will provide some context about hydrogen as an energy carrier. I'll move to talking about hydrogen energy in the UK. It's going to be very brief overview. And then finally, I'll provide 2 examples of research we are doing about systems integration of hydrogen. So I'm part of a research center called CYREX, which is the short for Center for Integrated Renewable Energy Generation and Supply. The CYREX established in 2008 as a multidisciplinary engineering research group. We do research across electrical engineering, mechanical engineering, and other disciplines. So anything related to energy supply and potentially demand, we are interested. And of course, we will collaborate not only within our center, but also with other colleagues within the School of Engineering, Cardiff University, and also nationally and internationally. Few topics that we are working on are shown here. So within our center, we have 11 academic staff, 20 postdoc, and around 40 PhD students. And they work on different topics as shown in this slide. I personally work on national energy infrastructures and mainly kind of working on electricity, gas, hydrogen, and heat networks. So in terms of energy infrastructure, the types of research we are doing is about interdependent energy systems, and that interdependence could be across different energy vectors, as I mentioned, electricity, natural gas, heating, cooling. and also it could be across different geographical scales, from building level to community and local to national and also international scale. So we develop modeling tools to better understand complex behavior of energy networks and the interaction between different types of energy networks. And those modeling tools are used to inform about short-term and long-term decision-making related to energy systems, short-term operational decision-making, and also long-term investment planning. We do collaboration with a range of different industry partners. National Grid and National Gas are two of the industry partners that we work with about and work on hydrogen systems. On top, few of the projects that we have been involved and we have led or provided. So HIACT is one of our recent projects. Actually, it is going to officially start on 1st of June 2023, and it is £10 million investment from Research Council UK, and this center is going to run for over 5 years in collaboration with several other universities in the UK, and also we have an impressive list of industrial partners on board. The idea of this center is kind of focusing on challenges related to systems integration of hydrogen. So we develop modeling tools in order to inform decision makers about investment decisions in this area. So I would like to actually start providing some brief background about hydrogen as an energy carrier. So as most of you know, hydrogen is the most abundant chemical element in the universe. Hydrogen is a very reactive element and very rarely can be found freely. On the Earth, vast numbers of hydrogen atoms are combined in water and hydrocarbons. So from these information, so the good thing is there are lots of hydrogens, which is really good in terms of actually having access to abundant source of energy. But at the same time, hydrogen cannot be found freely, which means we need some other feedstock or energy in order to decouple hydrogen from other elements and produce energy. From energy content point of view, hydrogen energy density, volumetric energy density is fairly low when we compare that with methane. It has almost 3 times lower volumetric energy density. So that means if we would like to provide the same amount of energy, we need to transport 3 times more hydrogen compared to methane, which it has some kind of operational challenges and consideration which need to be taken into account. Current demand for hydrogen globally is around 94 million tons. And mainly, this is the demand for refining and ammonia productions. The amount of low carbon hydrogen produced right now is less than 1%. So most of the hydrogen that currently are produced are using so-called gray hydrogen or using steam methane reforming of natural gas without capturing the CO2. And currently there is a very, very small amount of hydrogen produced and used as energy carrier. I mentioned about gray hydrogen, it is good to actually provide a bit more information about different ways by which hydrogen can be produced. Hydrogen is colorless, obviously, but the different naming convention has been used to identify different ways by which hydrogen can be produced. So here you can see different colors and technologies and feedstock or energy sources needed for producing hydrogen. Currently, most of the hydrogen are produced using this approach, natural gas reforming, without capturing CO2 produced by the process. But in order to move to net zero and decarbonize energy sectors, lots of emphasis are on low carbon hydrogen productions, including green hydrogen, which means using renewable sources of electricity and using electrolysis to produce hydrogen, or using blue hydrogen, which means using natural gas reforming and carbon capture and utilization, carbon capture and storage and utilizations in order to reduce the emission from the process. So as you can see, there are many different ways for producing hydrogen. On the demand side, in terms of application of hydrogen, hydrogen can be used in many different sectors, either as feedstock or as energy carriers. So from shipping to using hydrogen for power generations, or using hydrogen to produce heat, either high temperature heat or low grade heat for buildings. So there is a wide range of different applications. This diagram was produced by Leverage Associates. Again, this is what they think hydrogen would be competitive to be, the application that hydrogen is competitive, and down they think these are some application that hydrogen is not competitive, but overall I think there was some useful information in this diagram, but I think for hydrogen to be competitive, we really need to look at case studies. So it really depends on what case studies we are focusing on, and what are existing resources and potentials for producing hydrogen, and what are other alternatives that can compete with hydrogen. So this is quite general, but for different cases, this could be very different. In terms of transportation of hydrogen or storage of hydrogen, there are different technologies as well. Here, this diagram actually shows competitive transport mode for transporting hydrogen, depending on the volume of the hydrogen that need to be transported, and also depending on the distance over which hydrogen need to be transported. And one key point that I would like to actually mention here is that different pathways for hydrogen, from production to transport to storage, and also the application. There are so many different ways that hydrogen can be produced and used, and the best pathways for hydrogen really depend on several factors, including available resources and feedstock, cost competitiveness, availability of CO2 storage site, and also having certain level of demand for hydrogen. So and the best way to supply hydrogen really depend on case studies, and this is one of the research areas that we are very interested in working on. So to provide some background about energy systems in the UK and why hydrogen is being considered to be an option to contribute in achieving net zero. We need to first of all consider that achieving net zero by 2050 is a legally binding target in the UK. So and that means we need to make sure that all possible options can be taken into account, and they can play a role. So decarbonization of heat, transport, and industries in the UK currently is a big challenge. So the figure on the left-hand side shows the total electricity productions by different technologies and sources in the UK over the past 30 years. So as you can see, this part is electricity production by coal, which is almost very close to zero now. And that was because of some of these industrial emission directives and environmental legislation which require coal power stations to be decommissioned. But at the same time, electricity production using renewable sources are increasing significantly. Gas still had 30% share in the total electricity generation mix. So those changes on electricity sector caused the total emission from electricity sector to drop significantly over the past 30 years. So from 270 million ton of carbon dioxide to almost less than 100 million ton, which is significant. But at the same time, when we are looking at emission in transport sectors or in residential sectors, not much changes have been happening there. And these two sectors in particular are very crucial. The decarbonization of these two sectors are very crucial to help us achieve net zero. So hydrogen is considered to be one of the potential options for decarbonizing industrial sectors and also contribute to either producing low carbon electricity, providing heating for buildings, and also to be used for decarbonizing heavy good vehicles and potentially aviation or maritime. This diagram here shows illustrative hydrogen demand in terawatt hour, which is part of the hydrogen strategy published in 2021. The kind of range of demand envisaged by this strategy in 2030 and 2035 are shown here. So some sectors like industry and power sectors and also transport, as you can see, there are a kind of minimum amount of hydrogen demand, which is considered to be likely to achieve by 2035. But in the case of using hydrogen for heat, there are lots of uncertainties. And as you can see, the range of demand could be anything from 0 to 45 terawatt hour in 2035. The reason for that is, first of all, there are other alternatives like heat pumps, which could provide much higher efficiency, but that may not be suitable for all types of buildings. But at the same time, it is not very clear from policy point of view which directions we need to go in terms of decarbonizing heat in buildings. Another reason for that is there have been some kind of issues around public acceptability of using hydrogen in buildings, and there were some kind of issues with some of these new trials for kind of developing a hydrogen village in England, for example. One classic challenge regarding large-scale deployment of hydrogen is chicken and egg problem. So a minimum level of hydrogen demand is needed to justify investment in clean hydrogen infrastructure. And at the same time, without availability of hydrogen supply capacity, it is difficult to create demand. Right now, across UK, there are several projects ongoing and planned projects for either developing capacity for hydrogen productions or kind of using hydrogens to decarbonize some industries. These projects are mainly focused at local level, for example, industrial sites in South Wales, North East and Northwest of England. These are potential areas that they already have hydrogen demand, and that there are already hydrogen supply capacity in those areas, but it is mainly through a grey hydrogen, which is production of hydrogen using steam methane reforming without carbon capture and storage. So decarbonizing that hydrogen capacity is the first step. But then how to move from these smaller scale distributed hydrogen project into a more kind of larger scale nationwide hydrogen infrastructure has been a question which National Gas in the UK, that owns and operates high pressure gas transmission systems, try to investigate that in a project called Project Union. So I borrowed these figures from National Gas, and these are kind of illustrative representation of how they envisage hydrogen infrastructure and hydrogen supply demand can evolve over times in Great Britain. So 2022, the clean hydrogen production capacity was 0 gigawatt. The idea is to by 2025, 1 gigawatt hydrogen production capacity to be developed in these areas which are industrial clusters. So the hydrogen demand and supply already is there, but now by 2025, decarbonizing those is going to be the first step. Then later on, additional capacity of hydrogen productions, and as you might be able to see, because this is quite small figures, a pipeline for hydrogen to connect these two neighboring industrial clusters. And moving forward, again, introducing additional hydrogen production capacity, demand is going to take up, and more hydrogen pipelines are going to connect different regional clusters. And this is going to keep continuing, and more wind generation also, and also renewable generation technologies are going to be installed, which means moving toward more green hydrogen. And by 2050, around 64 gigawatt hydrogen production capacity to be installed. Most of them are going to be produced using wind, offshore winds, and in general renewable technologies, and kind of national hydrogen transport pipes also be installed by them. So very quickly going through some of the research that I'm doing in terms of energy system integration and hydrogen integration into energy systems. So this slide here shows energy flow in 2021 in the UK. It kind of shows where energy come from, how they are converted into different types of fuels and energy carriers. And on the right-hand side, we have different sectors that consume energy. If we want to describe this figure using few words, we probably will end up saying complex, interdependent, and potentially confusing. And these are exactly the point I would like to make here. So when we are dealing with energy system, we are dealing with a complex and interdependent system, and in terms of decision making and investment, sometimes it could be very confusing as well. And any changes in part of the system could have cascading impact on the other part of the systems. And what we would like to investigate in our research is how including hydrogen in this figure is going to affect the whole energy systems. So in order to unpack these complexity, we develop modeling tools. We develop modeling tools to kind of use mathematical formula in order to represent behavior of technologies, systems, networks, and so on. So the model is a representation of a system that is used to describe and explain phenomena that cannot be experienced directly. And to study this interdependency between complex energy systems, so we develop modeling tools, but we also need to be very careful about how we use this model and what types of questions, research questions, we can appropriately address using modeling tools. So as once said by George Box, a British statistician, all models are wrong, but some are useful. So that means we need to manage our expectation about the models and also be careful about how to interpret their output. Now, I would like to provide one example about some research we have done in this area, and this is a study we have recently completed looking at hydrogen as a source of flexibility. So, some context, larger scale and larger scale penetration of wind and solar in energy system is happening in the UK, and that means that they are variables and therefore they may not match demand. For example, this diagram here shows half-hourly electricity normalized electricity production using solar energy. So on x-axis we have hours of a day, and on y-axis we have months in a year. So when we are moving toward warmer colors, that means more electricity are being produced, which is in summer around noon. And when we are moving toward cooler color like blue, that means very small amount of electricity or zero electricity are being produced, which is usually around evening and morning in winter time. But what is happening is we have the maximum amount of electricity from solar PV around noon in summer, but the peak electricity demand in the UK is happening at around 6-7 p.m. in winter, where there is no electricity from solar. But also looking at kind of half-hourly variation and seasonal variation of demand and demand of heat and electricity in a year, we can see that the very large heat demand is happening in winter. So here we have January, February, March, and here we have November and December. So very significant heat demand there. But again, you know, if you would like to actually use solar energy, that is going to happen mainly here in the middle when we don't have much demand. So that highlights the importance of flexibility for short-term and also long-term balancing of electricity demand. And by flexibility here, I mean capability of the energy system to adjust its supply and demand in order to match them. So what is happening now is we are increasing our electricity demand because of electrification of heat and transport. We are increasing capacity of variable renewable technologies like wind and solar. At the same time, we are reducing capacity of controllable generation technologies like coal-fired power station and to some extent gas-fired power station. So the top two means we need more flexibility, but reducing the capacity of controllable generation technologies mean we have kind of reducing the amount of flexibility that we traditionally use. Now we need to look for alternative sources of flexibility. I would like to actually, I'm just looking at the time. I will skip this one, but so here we develop a modeling tool, a kind of a cost optimal modeling tool that take into account detailed characteristics of hydrogen energy system from production to transportation and also application. And on the other side, take into account different technologies for electricity generation, electricity network, and also demand for electricity. And in the middle, we have coupling component that connect these two systems together. And what we try to do here is to minimize the total operational cost of these systems, and at the same time making sure that energy demand is going to be met, physical constraints of technologies and network, and as well as kind of energy and mass balance are also going to be met. So we will do this by scheduling all these technologies across both systems. So I don't want to go into too much of details of what this figure on the right shows, but different sources of flexibility, including electrolyzers, air source heat pump, hydrogen boiler, and these air source heat pump and hydrogen boilers are important because they have access to thermal inertia of the buildings and using that thermal inertia of the building, they can adjust their hydrogen consumption or electricity consumptions. And by doing that, they can support the operation of both hydrogen and electricity supply systems. So yeah, we have different sources of flexibility there, and by kind of using those, we can reduce the amount of hydrogen consumption by hydrogen-fired power stations. We are going to reduce renewable curtailment, and also make sure that hydrogen supply and demand are going to be balanced. In this case study, when we look at that, initially we had 100 gigawatt-hour electricity importation from other countries, but by using these flexibility sources and making sure that we minimize curtailment of renewable generation, we could actually reduce this power importation to zero. This diagram here is one example of how flexibility from buildings could be useful in managing supply and demand across both electricity and hydrogen networks. So we have carried out some studies looking at almost 25 million residential households in the UK, and try to look at how we can use thermal mass of the building in order to provide upward or downward flexibility into the system for given outdoor temperatures. For example, when the outdoor temperature is -5, we can switch off heat pumps, and by doing that, it takes we can actually support the operation of electricity systems, and it takes kind of 1 hour, 2 hours before the indoor temperature of the building drop below 18 degrees centigrade, which can be considered to be too cold. So by adjusting this, we can provide flexibility to the system. Another modeling work that we have done was to address the kind of challenges related to injection of hydrogen into the gas network. So because one of the idea is we use the existing gas network and we start injecting hydrogen into different part of the gas network, and mix of hydrogen and natural gas can be transported using the same network. So our analysis showed that kind of mixing less than 20% hydrogen into the existing natural gas network does not need significant changes in the infrastructure in terms of capability of the system to meet the demand, in terms of capacity required for compressor stations. However, depending on where in the network we are injecting that hydrogen, that would cause a bit of inconsistency. So that means concentration of hydrogen in different parts of the network at different time of the day could be very different. So, for example, this one on the left-hand side showed when shows a case in which we inject hydrogen from these existing gas terminals. That shows that, okay, the hydrogen actually, the fraction of hydrogen in the gas is almost 20% across different parts of the network. Well, in this case, southwest and southeast, so these areas. The figure on the right-hand side shows distributed hydrogen injection, which means when we inject hydrogen from small-scale distributed sites, that is going to significantly affect the amount of hydrogen accumulation in different parts of the system, as you can see here. And there are some challenges here because of billing, because of appliances that we are going to use in different areas could be sensitive to the amount of hydrogen in the natural gas. So I would like to conclude my talk here by acknowledging the funders, Royal Academy of Engineering, and also UKRI to support some of the research that I've just gone through, and also National Gas that provided me a secondment opportunity. So I'm spending 50% of my time in hydrogen innovation team in National Gas over the next 2 years. Another point I would like to mention is, as part of HYACT, we are developing hydrogen project map which is an interactive online map. So you can actually have access to that using this QR code. And in case that you would like to actually let us know about some hydrogen project that is not already there, we would definitely appreciate that, and we will include this here. So I'll stop here. I'll hand back to Omar. Thank you very much.
Thank you very much, Meysam, and thank you, Eugene. That was a fantastic seminar. So fantastic to see the comparisons between the UK and the US. So also, Marcello, thank you for your positive comments on the talk. So if people have any questions, you can put it in the Q&A box right at the end, or I will be asking both of you a question in a minute if nobody puts their questions first. So one question I had put to you, both Eugene and Meysam, is that one aspect of hydrogen is hydrogen storage, right? Because hydrogen is a very light gas. So, in order to store it in an appropriate place, and ensuring also that when you transport hydrogen, I believe you can also transport in liquid form. So there was very little coverage. I can see trains full of hydrogen rather than coal, but surely there are lots of safety and stability issues in transporting hydrogen. So what were your thoughts on that from a UK and US perspective? Meysam?
Yeah, I can go first, and then Eugene, please contribute. I think in the UK, there are a lot of emphasis on long duration storage and the role of hydrogen in providing seasonal storage. Because when we talk about hourly balancing of supply and demand, we have access to battery storage, which could be more competitive if we want to compare the round trip efficiencies. But hydrogen is quite competitive when we talk about seasonal storage. And right now in the UK, there are projects looking into storing hydrogen in salt cavern. And also there are some plan for converting rough storage, which used to be the largest natural gas storage in the UK, which is now decommissioned. So converting that into hydrogen storage. So the focus in the UK is mainly on using hydrogen for long-term storage.
So in the United States, it is actually growing in all directions. It's not just long-term seasonal storage. We do have very large facilities that are already in operation by Linde in Gulf Coast, and these are dome salt caverns that are used to store hydrogen for long term. And there is about 1,600 miles of pipelines that actually connect those facilities, and they're in existence today. Also, we do have an industry that is growing today. There is existing capacity to move hydrogen about. So there's both cryogenic or compressed storage, and I could talk in a lot more detail. I do have actually slides on that particular area. But today, we are adding to the capabilities and capacities of the companies actually moving into this direction and innovating very rapidly. And so there's a number of new technologies that exist to store compressed hydrogen in tanks that could be placed on different platforms like rail or like trucks. And so today we see this sector actually exploding. And again, I can name companies, but probably not worthwhile going in that direction. So also there is a alternative way, and Meysam mentioned that as well, of moving hydrogen about. And so it's not only just a liquefied form, means that you need to apply cryogenics. That's why it's very important, expensive. But there's another way to do it, is moving into via methanol or ammonia. That is another sector that is growing. There are some limitations on moving those things about and how you can use the hydrogen later. And also there's energy penalty and so on and so forth. But again, like anything we do, it's a complex ecosystem. But hydrogen, the kind of alluring thing is that actually there is a flexibility of moving it about.
Okay, great. Thank you very much, Meysam and Eugene. So I don't see any more questions. So this is the first of a seminar series in hydrogen. I hope we will unpick, some of the ideas that you mentioned. I have a lot of questions, Eugene and Meysam, when you were presenting. I was thinking of, hydrogen as a byproduct of agriculture, the idea of using hydrogen as a way to improve ammonia, which is also a mechanism to support better agriculture. I hope that we will be able to pick up on some of these themes, as we go through this seminar series. So thank you so much. And I believe, sorry, my son, go ahead.
Very quickly, because the next presenter for next month from Cardiff is our colleague, Professor Agustin Valero Medina, who is going to actually talk about hydrogen and ammonia specifically.
Oh, fantastic.
Fantastic.
I
Excellent.
think that's fantastic because I think both Wyoming and Cardiff has strong agricultural communities, and also utilizing ammonia as a vector is very, very interesting. So we look forward to that talk. I believe this presentation will also be made available as a recording. So we will share the link very widely. So thank you so much for both of you for giving a great talk. Thank you.